Recall that an ionic compound is made of positive and negative ions attracted to one another. Those positive ions are called cations. Cations form when atoms lose electrons. So these are going to be metal ions, or it could be a clump of those polyatomic ions with an overall positive charge. The negative ion is called an anion. And an anion is a negative ion that is a result of a nonmetal gaining electrons. Or that anion could be a negative polyatomic ion. And so in an ionic bond, there is a very strong attraction between the positive cation and the negative anion. And today we're going to learn how to write the chemical formulas for ionic compounds. So recall, when we name ionic compounds, we do not use prefixes. There's no use of mono, di, tri, tetra, penta, etc. So when I'm given the name of an ionic compound, how is it then that I know how many of each cation and how many of each anion I'm supposed to write in that formula if the name doesn't have any prefixes to tell me the subscripts of each one of those ions? So we do have to use the charge of the cation and the anion to figure out the correct ionic formula. And there's one general rule we have to follow when writing ionic formulas. And that rule is that ionic compounds are neutral, which means there is no charge to the compound. In other words, the positive and negative ions must cancel out. They must cancel each other out. For how much positive charge we have to have the same equal negative charge. So this one rule governs how we go about writing formulas for ionic compounds. So let's take a look at some examples. Number 1, lithium phosphide. First of all, I recognize this as an ionic compound because lithium is a metal and phosphide is a non-metal. So I know that this is ionic, and obviously we don't have prefixes in the name. So how is it that we're going to write the chemical formula if the name doesn't have prefixes to tell me how many lithiums and how many phosphides? Because this is ionic, I have to first write the charges of the lithium ion and the phosphide ion. So lithium Li, on the periodic table, I locate lithium. It's in the first group, the first column on the left. That's going to have a 1 positive charge. Locate phosphorus on the periodic table. And I know that this is going to be phosphorus from the periodic table because I have an "ide" ending here. So it's just phosphorus. Locating phosphorus on the periodic table, I note that it has a 3- charge. And remember our one rule to writing ionic formulas. The positive charge must be equal in magnitude to the negative charge. You see here, 1 positive and 3- are not going to cancel each other out. They're not equivalent in magnitude. So let's figure out how many of each one we're going to need in order for their charges to be equal but opposite. So I'm just going to draw a little chart here. If 1 lithium carries with it 1 positive charge and 1 phosphide ion carries with it 3 negative charges, all of this is 1 phosphide, 3 negative. You can see here that the charges do not cancel each other out equally. we have some leftover negative charges. And so I'm going to add 2 more lithium ions so that now I have a positive for every negative charge. And so this is what we mean by equal but opposite. I have 3 positive and 3 negative. And so everything cancels out. I have a neutral compound. So I'm going to count how many lithiums I ended up using in order to get this cancellation. I used 1, 2, 3 lithiums. So the subscript of lithium is a 3, and I used just 1 phosphide. So its subscript is 1. And we know that in our final answer, we typically do not write a 1. It is understood to be a 1. So this would be my final answer. That would be the chemical formula for lithium phosphide. And I'm emphasizing here that I did use just phosphorus because the ending here was IDE, which means it's one element from the periodic table. Okay, let's try another one. Example number 2, barium sulfate. So I see here, I have barium, which is a metal, and I have sulfate, which is a polyatomic ion. So I know I have an ionic compound. Again, no prefixes appear in the name, so I need to know the charges of each one of these ions in order to be able to write the correct chemical formula. So I'm going to look at my periodic table for barium. Barium is in group 2, so it carries a 2 positive charge. Sulfate is not on the periodic table. Sulfate is a polyatomic ion. So that ATE ending, ATE, usually means we have a polyatomic ion. Those are going to be one of the 9 that we have memorized. And so I just have to know that sulfate is SO4 to negative. Okay, so the chemical formula of sulfate is SO4, but because it's an ion, it has an overall charge, and for this particular one, it has a 2 negative charge. Now, the way we use this to write an ionic formula, we still follow the same rule. All the positive charge has to cancel out all the negative charge. And so I can see here with my charges, barium is a 2 plus, sulfate is a 2 minus. Hey, those are already equal but opposite to one another. So I'm only going to need one of each. But if you wanted to see the ions drawn out, we can do that. One barium ion consists of 2 plus charges. One sulfate ion consists of 2 negative charges. And you can see here that I have a positive and a negative that are going to cancel out. And then I have another set. A positive and a negative are going to cancel out. I have the same number of each positive and negative. And so how many barium ions did we use? We used just 1. How many sulfates did we use? We just used 1. And so our final answer is 1 barium and 1 sulfate. Now, a word about these parentheses around polyatomic ions. I'm writing parentheses around SO4 here, the sulfate, for emphasis that that's a polyatomic ion. When technically, I don't have to write those parentheses. It is totally acceptable to leave out those parentheses. This is also correct. But for emphasis here, I'm going to put in the parentheses just so that we are recognizing that that's a polyatomic ion. As you practice more, you're going to end up leaving off these parentheses as you get more and more comfortable with it. All right, let's try another one. Number 3, magnesium nitride. Magnesium is a metal. Nitrogen is a nonmetal. So again, I have an ionic compound. Notice no prefixes in the name. So I know I'm going to have to use charges to help me figure out the formula of this compound. And so magnesium is Mg. That comes from the periodic table. I look at where it's located. It's in group 2. It carries a 2 positive charge. Nitride, the ID ending here. Remember, ID means from the periodic table, a singular element from the periodic table. This is not one of those polyatomic ions. So just regular old nitrogen here. Nitrogen, look at where it is on the periodic table. It has a 3 negative charge. Okay, pause, reflect. Do you have equal but opposite charges? Nope. I got a 2 and I got a 3. Those are not equal to one another. So I got to figure out how many of each one we're going to need. So I'm going to draw this out. For one magnesium, it carries 2 plus signs, okay, 2 positive charges. For one nitrogen, that one nitrogen carries with it 3 negative signs. I'm going to start canceling things out. For each positive that I have a negative, they cancel each other out. And so I can see here, I got a negative left over. So that means I'm going to have to add some more positive charge to cancel it out. And so my magnesium, I got to add another magnesium. But each magnesium contributes 2 positive signs. I can't just add 1, okay, because that's not the charge of magnesium. I have to add 2 plus signs because that is the charge of one magnesium ion. I can't change the charge. And so I can see here, all right, great. That negative sign, that negative charge, whoop, canceled out. Okay, with that positive sign. Okay, but now I run into another issue. I got an extra positive. So that means I got to add some more nitrides. But each nitride contributes 3 negative charges. I can't change that. Okay, so now, whoop, we cancel out that last plus sign. But we run into another issue. I have 2 negatives left over. And so that means I got to add in some more magnesium positives. And each magnesium carries with it 2 plus signs because that is its charge. It is a 2 plus charge. Now I can see here, everything cancels out. I have a total of 6 plus signs and 6 negative signs. So that's what we mean by equal but opposite. You're going to end up with no charge, a neutral compound. And so let's count them up. How many sets of magnesium 2 plus ions did we use? 1, 2, 3. So that's going to be Mg3. And then how many sets of nitride 3 negative did we use? We used 1, 2. So that's going to be N2. And so my final answer will not contain the positive and the negative charges. I just want how many magnesiums and how many nitrogens. So my final answer is Mg3N2. All right, let's try another. Iron 3 chlorate. That's iron, parentheses, Roman numeral 3 inside those parentheses. Well, iron is a metal. Chlorate is a polyatomic ion. I know that. I see ATE at the end. I know ATE is going to be a polyatomic ion. One of those 9 that I have memorized. And so again, this is ionic because I have a metal and a polyatomic ion. So I have to use charges to write the formula of this compound. So we start with our iron. Iron is Fe. And you'll note that I have a Roman numeral 3 in parentheses. And that's because iron is a transition metal, and recall that transition metals, their charges vary. So we have Roman numerals that tell us what charge that particular transition metal is going to have in that particular compound. So that Roman numeral 3 translates into a 3 positive charge on the iron. The Roman numeral is always positive. Okay, so that 3 Roman numeral is turning into a 3 positive charge. Roman numeral just means the charge of the transition metal. Now for the chlorate, it's a polyatomic ion. I have to recall that chlorate has a formula ClO3, and overall its charge is 1 minus. Now that I have the charges of both my cation and my anion, I look at those charges. Are they equal and opposite? Nope, they're not equal and opposite, so I gotta figure out how many of each one to use. And so I'm gonna draw my picture again. 1 iron carries with it 3 plus signs because it's Fe to the 3rd plus charge, or 3 positive charge. And then 1 chlorate carries with it 1 negative. Because its charge is 1 negative. And so I can see here, all right, I got a positive and a negative, they cancel out, but then I got 2 extra positive signs. Okay, so we're not at a point of neutral compound yet. So let's add another chlorate. When I add a chlorate, I add 1 negative sign because that is the charge of that chlorate. Okay, that second positive ion is gone. And now let's add another chlorate. And we cancel out that 3rd positive sign. And so you can see here, we're now at the point where we are equal but opposite in charge. I have 3 plus signs and 3 negative signs. We are done. And so now let's count how many of each one we used. We used just 1 iron. And I used 1, 2, 3 copies of the chlorate. And so my final answer is going to be Fe parentheses ClO3 close parentheses, and I put a 3 on the outside to denote that we used 3 copies of that chlorate. For this polyatomic ion, we must use parentheses in this scenario. You have to use parentheses when you have multiple copies of the polyatomic ion. Okay, if you're using more than 1 copy of that polyatomic ion, you gotta put parentheses around the formula of the polyatomic ion and then the number of copies you used on the outside. So this 3 that I'm writing on the outside corresponds to the 3 copies of chlorate that we had to use to write this formula. Okay, so we have to use parentheses for polyatomic ions anytime that we have multiple copies being used of that polyatomic ion. The only time you can omit parentheses around a polyatomic ion is when you're only using 1 copy. So in summary, for ionic formula writing, positive and negative charges of those ions must be equal but opposite. If you see "ide," more than likely it's that one element from the periodic table. Just be careful, there are a couple polyatomic ions that end in "ide," but 98% of the time you see "ide," one element from the periodic table. If you see 8 ATE, that's a polyatomic ion. Refer to your polyatomic ion sheet. Use parentheses for polyatomic ions. When you see a Roman numeral inside of parentheses, that is the positive charge of the metal ion. And Roman numerals are used by transition metals and then also tin and lead. There you have it. Quick overview of how to write ionic formulas. The more practice that you do, the more comfortable you're going to get at this skill. It takes some practice. Feel free to return to this video at any time to see the examples again and to hear those explanations again. Now go practice.